So with properties of rational exponents, how will we use properties of not just rational exponents, but properties of exponents that we've learned in the past to evaluate and simplify expressions? So we're going to review exponent rules. First rule is a product of powers property. We've already been exposed to this rule. A to the m times a to the n means you're going to add those exponents. So for example, if I have the same base of 3's, I could just add those exponents. 2 plus 7, leaving me with 3 to the 9th, which if I need to plug it into my calculator, I can and move on. So then the power of a power property. We already have discussed this as a strategy last Friday to, if I needed an x by itself or so on. But we multiply powers. So for example, 5 to the 2nd raised to the 4th power, you just multiply those powers and whatever. If you need to calculate it later, that's fine. Power of product, though, we haven't really been exposed to this too much, but if you have something inside parentheses raised to a power, you can distribute that power. So for example, if I had 2 times 3 raised to the 6th, then that means it's 2 to the 6th times 3 to the 6th. Quotient of powers property. If you have a quotient, then you can take the numerator exponent minus the denominator exponent. So for example, let's say we had 3 to the 7th over 3 to the 5th. That's the same as 3 to the 2nd. All right, but what if that fraction was in parentheses raised to a power? Similarly, I can take that entire fraction and raise each individual numerator to the power, denominator to the power. So for example, if I have 4 fifths to the 3rd, each of them gets raised to the 3rd. Anything to a 0 power is 1. Anything to the 0 power is 1. We're going to keep that in mind. And this may be the one thing we definitely need to write down because it's for some reason the one we forget. If you have a negative power, then that means it's the reciprocal of that. For example, if I have a to a negative n, that's equal to 1 over a to the positive n. So let's get down these instructions. Use the properties of rational exponents, or in this case, we're just going to use the properties of exponents to simplify the expression. So in the first case, x times x to the 1/2, I notice they are both the same base, and this x is raised to the first power. So using, let's see, the product rule of the same base, that's going to be x to the 1 plus 1/2 power, which is the same as x to the 3/2 power. I could either write my answer like this, or I could write it like this, but which one looks more simple? First way looks a little bit more simple, less characters. Next one, number 2. If you have 4 to the 2/3 powers raised to the 6th power to a power, you're going to multiply those powers. So 4 to the 2/3 times 6. Let's simplify that product. Let's see, cross cancel. If I cross cancel, we get a 2 here. So this is like 4 to the 4th power. I could either stop here. Actually, I guess if I want it definitely simplified, 4 to the 4th. 64 times 4. 256. So I'm okay with 4 to the 4th just because we're practicing exponential rules and you got down to a number to an exponent. All right, let's do this some more. With this quotient, using old rules, I can take the numerator exponent minus the denominator exponent. So we've got y to the 1/3 power. I could either write it like this, or I could write the 3rd root of y. Number 4, 1 over 64 to the negative 1/3. Wait a second, I have a negative power. So first I need to write it as, in the numerator, 64 to the positive 1/3. And 64 is one of my numbers in that list. 64 is one of my numbers in that list. That's the same as 3rd root of 64, which is 4 times 4 times 4. That's the same as z to the 2/3 plus 1/2. You may need your calculator for that. I don't know. But if you want to quickly get a common denominator is 6, and then you multiply the numerators by what they don't have. So it turns into 4/6 plus 3/6. That's a total of 7/6. If you don't believe me, you can check it on your calculator. So in this next example, you have the third root of 16 times the third root of 4. There is a rule that if you have two things, first off, you got to note the multiplication. If it was addition, you'd be adding like terms, and these would not be like terms. But it's multiplication. Make a note of that. When it's multiplication, I can take them both underneath the radicand third root. Since their indices match, when indices match, you can put them under the same index with their product. So underneath there, we get the third root of 64, which is a perfect root. We get 4. So if it's multiplication between two of the same indices, we can take them both under one cubed root. Same with number 7. They both have fourth roots, so we can put them under one fourth root and just take their quotient. So 32 divided by 2, we're looking at 16 there. Fourth root of 16, that is a perfect fourth root. It's a fourth root of 2, or fourth root of 16 is 2. So third root of their quotient, 250 halves. Looking at the third root of 125, which is one of those numbers we need to memorize. Third root of 125, we're looking at 5. Third root of 32, however. So here's where we call it rationalizing. 32 is a nice number. The bad thing is 32 is a perfect fifth root. It's not a perfect third root. So this is where we're going to rationalize. We're going to find a perfect third root within 32. So if we start doing the factor tree, like 4 and 8, 2 and 2, and I know 8 is 2 times 2 times 2. Notice how, the index is 3. The index is 3, so I'm circling a group of 3. That means I have a perfect cubed root that comes out to be a 2, and then notice what's going to be left. So this is going to be, we have a perfect cubed root, and then we're left with 2 on the inside, 2 2's on the inside. So it's 2 times the third root of 4. Let me show you another way we could write that. So this is the same as like 2 to the third power times 2 squared. If you broke it up into perfect third roots. If I were to separate them into 2 third roots, we have 2, or third root of 2 cubed times third root of 2 squared. Still turns out to be, wait a second, third root of 2 cubed undo each other. And I'm still left with 2 times the third root of 4. So we're going to practice rationalizing a little bit more. So this first index says, hey, get groups of 4 going. So if I separate 256, I know 256, just because we've done it a lot now, is 16 times 16. 16 breaks up into 4s, which breaks up into 2s. This index is saying circle groups of 4. So I've got one group of 4, I've got another group of 4, so it's going to be perfect fourth root. So x to the 8th could be x, 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 and you keep going till you have 8 of them, and you've got one pair of x's and another, I shouldn't say pair, a group of 4 and another group of 4. So that also turns out to be, if you have 2 groups coming out, that's x times x, otherwise known as x squared. And then you try to break down the y's, but they don't break down into anything, so that is staying inside. On 11, I'm just going to break them up into 2 square roots. I'm going to have square root of the numerator, which is 4x squared y, square root of the denominator, 9z squared. And then I'm going to take the square root of each. In the numerator, the square root of 4 is perfect, that's a perfect 2. Square root of x squared, that's a perfect x, but I'm left with a y on the inside still. And in the denominator, I have a perfect 3z. So this is the case when, if you've got adding or subtracting, make a note of this. This is subtraction. I'm doing like terms. It's like you have 2 of these, fifth root of x, or fifth root of 3. So if you had 2x minus the same term, if you subtract those, you're left with only one of them. So I'm left with 1 fifth root of 3. Notice how I do nothing with the radical. Nothing with the index. So wait a second. 7 times 2 to the 1/8. 2 to the 1/8 is a root. That's like the 8th root of 2. You can't do anything with that with an addition sign. So because I'm adding 7 of these plus 4 of these, that means I have a total of 11 of these. Notice how I do nothing with the radicand 2, or the base 2, and the power 1/8, or the root 8. And just like when we did Pythagorean theorem, 4 times the square root of x plus 2 times the square root of x, you just start adding like terms. I do nothing with the radicand x, nothing with the index 2.